Somewhere in Shenzhen, behind unmarked doors and under fake employee identities, a machine has been running for months that was never supposed to exist outside of one country. A machine that took the Netherlands 2 decades and roughly $10 billion to build. A machine so precise that its mirrors are polished to an error smaller than a few atoms. And according to a Reuters investigation, China has now built one. Not a blueprint, not a simulation. A working prototype that is already generating the single hardest form of light on Earth to produce on demand. For 19 years, exactly one company on the planet could do this. That number is about to change, and the way it changed is stranger than anyone expected. This is not a rumor from an anonymous forum or a state media press release dressed up as a breakthrough. The reporting traces back to sources with direct knowledge of the project, and it names real institutions: the Shanghai Institute of Optics and Fine Mechanics, the Harbin Institute of Technology, Tsinghua University, and companies including Huawei and SSMB, China's homegrown lithography champion. ASML itself, the Dutch company that has held a global monopoly on this technology, acknowledging that others would naturally want to replicate what it has built. Christophe Fouquet, ASML's CEO, said as recently as April that China would need many, many years to pull this off. The prototype in Shenzhen suggests that clock may be moving faster than he expected. To understand why this matters, you need to understand what an EUV machine actually does, because the process sounds almost like science fiction until you break it down. Imagine trying to carve the world's most detailed engraving, but the tool you're using has to be a wavelength of light narrower than almost anything visible, and you have to fire it with pinpoint accuracy 50,000 times every single second. All day, every day. That is roughly what happens inside an extreme ultraviolet lithography machine. A microscopic droplet of molten tin, smaller than a grain of sand, is fired through a vacuum chamber. A laser hits it twice in rapid succession, first to flatten it into a disk, then to vaporize it into plasma. That flash of destruction releases a burst of ultraviolet light at a wavelength of 13.5 nanometers, and that light is what gets funneled mirror by mirror onto a silicon wafer to etch circuits finer than a strand of human DNA. It is controlled explosion used as a drafting tool, repeated with a level of precision that engineers have compared to shining a flashlight from Earth and hitting a coin on the surface of the moon. Here's where the scale of this really lands. ASML's own numbers put more than 6 billion euros and roughly 17 years into EUV research and development, with additional co-investment from Intel, TSMC, and Samsung, pushing the total closer to $10 billion. 17 years. That is longer than some of the engineers working on China's prototype have been alive. And it is not just money and time, it is also physical precision that borders on the absurd. The mirrors inside an ASML machine built by Germany's Carl Zeiss are so exact that if you scaled one up to the size of Germany itself, the largest bump on its surface would still be under a millimeter tall. This is the machine China is now trying to replicate, not from a public manual, but largely by reverse engineering and years of quiet recruitment. To put ASML's dominance in context, it helps to compare it to something more familiar. Imagine every smartphone, every data center, every advanced fighter jet radar system, and every AI model on Earth, all depending at some point in their supply chain on parts manufactured with tools built by a single company in a single small country. That is not an exaggeration. It is roughly the actual situation the world has been operating under since 2007. And it took ASML about as long to perfect that technology as it took the Apollo program, the moon landing, and the entire subsequent decade of NASA's shuttle-era missions to unfold, one after another. 17 years of grinding, incremental engineering, most of it invisible to the public, building toward a machine so specialized that fewer than a few hundred people on the planet fully understand how every subsystem inside it works. Now here's the part that connects the two stories most people are missing. This breakthrough did not appear out of nowhere in 2026. It followed years of slower, less glamorous progress that most of the world ignored. Earlier this summer, a separate Chinese company, Shanghai Aishengya Electronic Technology Group, began producing its own deep ultraviolet, or DUV, lithography machines. The older, less advanced cousin of EUV that is still used to make the majority of chips in cars, appliances, and mid-tier electronics. The news sent ASML's stock tumbling as much as 8% in a single day. Aishengya reportedly plans to build around 5 of these machines this year and about 20 in 2027, a fraction of ASML's planned output of roughly 130 DUV systems in 2026 alone. But the symbolism mattered more than the numbers. For the first time, a Chinese company was shipping working immersion. Lithography tools to major domestic chip makers, including SMIC, Hua Hong Semiconductor, and Changshin Memory Technologies. That DUV milestone is where most analysts assume the story would stop for years. DUV and EUV may sound similar, but the gap between them is enormous. One produces light using a relatively conventional laser process refined over decades. The other requires vaporizing metal into plasma with atomic level control. Ricardo Hori, an analyst at Audio BHF, put it bluntly when the DUV news broke. EUV, he said, is a completely different technology, and he doubted China could cross that gap anytime soon. That was the consensus. And then, within weeks, a very different report started circulating, one about a secret facility in Shenzhen that had already gone further than anyone outside the project realized. According to Reuters' sourcing, the machine at the center of this story was completed in early 2025 and has spent the time since then in quiet testing, occupying nearly an entire factory floor inside a highly secured building. The team behind it is reportedly composed largely of former ASML engineers, brought together with state research institutions in a deliberate fusion of private expertise and national strategy. Workers on the project were reportedly issued false identities specifically to keep the effort concealed. Whatever you think of the ethics involved, that level of operational secrecy tells you how seriously Beijing is treating this as a matter of national security, not just industrial ambition. Let's slow down and look at what the machine can actually do right now, because this is where the story gets more complicated than the headlines suggest. The Shenzhen prototype reportedly generates EUV light at the correct 13.5 nanometer wavelength using laser-produced plasma, the same fundamental method ASML uses in its production line twin-scan machines. That detail matters, because it strongly suggests the design leans heavily on studying and possibly reverse engineering ASML's own architecture rather than inventing something built from scratch. At the same time, separate Chinese teams are pursuing genuinely different approaches in parallel. Researchers connected to the Harbin Institute of Technology have been developing a discharge-produced plasma light source, while a team at Tsinghua University has been experimenting with an entirely different physical method called steady-state microbunching, which uses a particle accelerator instead of a laser to generate EUV light. Conversion efficiency of 3.42% using a solid-state laser design that ASML itself tried and abandoned years ago for being too inefficient to scale. That number 3.42% might sound small. It is not small. It is close to the threshold multiple engineering teams have identified as the point where a light source stops being a laboratory curiosity and starts being viable for real manufacturing. 3.42% efficiency. On a method the industry leader had already thrown away as a dead end, that is the kind of number that makes seasoned analysts sit up, because it means Chinese researchers are not just copying ASML's homework. In at least one corner of this race, they may be solving a problem ASML decided wasn't worth solving. It also illustrates something important about how this whole effort is structured. Rather than a single team chasing a single design, China's approach looks more like several competing bets running in parallel. The reverse-engineered laser-produced plasma prototype in Shenzhen, the discharge-produced plasma work out of Harbin, the particle-accelerator-based steady-state microbunching research at Tsinghua, and the solid-state laser refinement at the Shanghai Institute of Optics and Fine Mechanics. Why one of these paths failing would not end the program, because the others keep advancing independently. That is a very different risk profile than a single company betting everything on one architecture, the way ASML effectively did in the 1990s and 2000s. Let's pause and recap what we actually know so far, because a lot has been thrown at you in the last few minutes. A domestic DUV machine is already shipping to real Chinese chipmakers, years ahead of where most analysts expected. A prototype EUV machine is already generating light at the correct wavelength inside a secret facility in Shenzhen. And at least one alternative light source approach has crossed an efficiency threshold that ASML itself once considered a dead end. 3 separate storylines, 3 separate institutions, all converging on the same. Conclusion. The timeline for closing this gap just got shorter than almost anyone in the industry predicted a year ago. So the question becomes, what is still standing in the way? And just how big is that remaining gap, really? But before this starts to sound like China has already caught up, it's worth pausing here for a signpost. Because the next part of the story is where the honest limitations come in, and they are significant. The single hardest unsolved problem is not the light source at all, or it is the optics. Generating a burst of EUV light is one achievement. Focusing and directing that light with the atomic level precision needed to reliably print billions of transistors onto a wafer over and over for years without drift or contamination is a different challenge entirely, and it is the one ASML spent the majority of its 17 years solving through its partnership with Zeiss. There is no confirmed public reporting that China has replicated mirrors anywhere near that tolerance. Debris from the vaporized tin droplets constantly threatens to coat and degrade the collector mirrors inside any EUV system, which is one reason ASML's machines require such extraordinary engineering just to keep running reliably at 50,000 pulses a second. Building a light source is, in the words of more than one industry analyst covering this story, the easier half of the problem. This is also the point where the caveats need to be stated plainly, because hype without honesty does a disservice to a story this significant. According to the Reuters report and subsequent industry analysis, the Shenzhen machine has not yet produced a functional chip. It has generated EUV light. It has not demonstrated the sustained industrial-scale reliability that turns a laboratory prototype into a production tool capable of manufacturing at commercial yield. China's own government targets reportedly aim for chip production on a domestic EUV machine by around 2028, while independent industry forecasts, including analysis from SemiAnalysis, place a more realistic timeline closer to 2030 for anything resembling commercial viability. And this gap is not unique to EUV. Even on the more mature DUV side, where China already has working machines shipping to real customers, a columnist writing from Liaoning noted that the domestic 28 nanometer DUV tool still lags roughly 4 generations behind ASML's current lineup, with performance closer to what ASML was producing about 15 years ago. Some of the underlying breakthroughs in DUV immersion lithography do carry over toward EUV, according to analysts like Dan Triolo of the Albright-Stonebridge Group, but many do not, since the light source and optical requirements at the EUV level are, in his words, considerably more advanced and more complex. In other words, mastering the older technology gives China a running start, not a finish line. There's also a deeper question worth sitting with here, one that goes beyond timelines and efficiency percentages. Is this genuine innovation? Or is it an extraordinarily fast, extraordinarily well-funded act of reverse engineering built on the back of 2 decades of Dutch, German, and American research? ASML has a documented history of pursuing legal action over exactly this kind of concern. In 2019, the company won an $845 million judgment against a former Chinese engineer accused of stealing trade secrets. And that case is part of a broader, well-documented pattern of espionage allegations trailing the company for years. Nobody covering the story, including the analysts most impressed by China's progress, is claiming this prototype represents pure indigenous invention untouched by outside knowledge. To be clear, that distinction matters less for the physics and more for the geopolitics. Because whether a technology is invented from first principles or painstakingly reconstructed from studying someone else's decades of work, the strategic outcome for global chip manufacturing ends up looking remarkably similar either way. It's also worth being precise about what catching up would even mean in practice. Because EUV lithography is not a single finish line, it's a moving target that ASML itself keeps pushing forward. Even as reports of China's prototype circulated, ASML was already shipping its newer high-NA EUV systems to customers like Intel, a more advanced generation of the same technology capable of even finer transistor patterns than the machines China is still trying to replicate. That means China isn't just chasing a stationary target from 2019, it's chasing a target that keeps moving further away each year ASML keeps innovating. Analysts at SemiAnalysis, the research firm that has tracked this race closely, have pointed out that tool performance is only O&E piece of the puzzle. Scaling production of the machine itself, building a reliable supplier ecosystem around it, and achieving the kind of fleet-wide consistency ASML has spent decades refining all stack up as additional hurdles on top of the core physics. A single working prototype in a secured lab is a meaningful milestone. It is not the same thing as a fab floor full of machines running around the clock at commercial yield. So where does that leave the broader picture? For nearly 2 decades, EUV lithography has functioned as the single tightest choke point in the entire global technology economy. The recent export restrictions on ASML machines have been treated by Washington as one of the most consequential levers in the entire US-China tech relationship. Every advanced AI chip, every cutting-edge smartphone processor, every next-generation data center accelerator ultimately traces back through this one narrow bottleneck. If China's timeline holds anywhere close to 2028 to 2030, the bottleneck stops being absolute, and the entire structure of export controls that Western governments have built their strategy around starts to look considerably less durable. That is not a small shift. That is potentially one of the most consequential changes to the global chip supply chain since ASML's monopoly began in the first place. If this story has grabbed your attention, it's worth sticking around, because the next question is the one nobody has a confident answer to yet. What happens to the balance of global chip power if China actually hits its 2028 target instead of slipping to 2030 or beyond? None of this happened in isolation either. It arrives against a backdrop of tightening restrictions, deepening distrust, and a semiconductor industry that has quietly split into 2 competing technological spheres. What one industry publication has started calling a silicon curtain, descending across the global chip supply chain. On one side sits the established order. ASML, Zeiss, TSMC, Samsung, Intel, decades of accumulated precision engineering that recruit aggressively and accept years of failure in pursuit of a single strategic outcome, technological independence from a choke point that Beijing has decided it can no longer tolerate depending on. Think about what that independence would actually unlock. Companies like SMIC and Huawei have spent years designing based multi-patterning techniques because EUV tools were simply off the table under export restrictions. A domestic EUV supply chain, even an imperfect one, would remove that ceiling. It would mean Chinese chip designers could finally build hardware to match their own ambitions, instead of designing around a manufacturing bottleneck imposed from outside the country. That is precisely why Washington has treated ASML's export licenses as one of the sharpest tools in its entire strategic arsenal, and it's exactly why a single secretive lab in Shenzhen has become... There is a natural instinct, watching a story like this unfold, to reach for the most dramatic possible framing. Either total panic that the West's advantage is collapsing overnight, or total dismissal that this is nothing more than propaganda. Neither reaction survives contact with the actual reporting. What the evidence supports is something more measured and, honestly, more interesting. A determined, well-resourced, multi-pronged effort that has closed real distance on a problem long assumed to be unsolvable. Outside of one small country in Europe, while still facing the same brutal engineering wall, atomic precision optics, contamination control, and years of accumulated manufacturing know-how that has kept this technology a monopoly since 2007. Let's bring this back to where we started. A hidden lab, false identities. A machine that took one country 2 decades to perfect, now apparently running in prototype form somewhere it was never supposed to exist. The honest version of this story sits between the two extremes you'll find online. It is neither proof that China has already caught up to ASML, nor is it something to dismiss as propaganda or exaggeration. It is a genuine, verifiable step, sourced through credible reporting and corroborated by named institutions, toward closing a gap that the world's leading semiconductor analysts thought would take until the mid-2030s to even approach. Whether that gap closes in 3 years or 10, the fact that it is closing at all changes. The calculation for every government, every chip maker, and every company whose products depend on the machines inside that one narrow, atom-precise bottleneck. Tell us in the comments which facts surprised you more. That China's prototype is already generating real 13.5 nanometer EUV light, or that even after doing that, it still hasn't produced a single working chip.